start recording. Thank you. I almost forgot again. So we have a vector field. So this is just the problem from the text. We have R, which is a parameterization of a surface. This one, unlike the ones I made up, actually represents something. So you can see this is z is equal to 4 minus x squared minus y squared. Nope. All right, so I try again. I reloaded. Can you hear me now? Okay. So this could be an we might not get a huge amount done today because it seems like the connection isn't great. So here what we want to now find is find the flux through this paraboloid. And the process here is first we have to get a normal vector. And we do that by looking at the partial derivatives of the parameterization. So take the derivative of r with respect to u. Take the derivative with respect to v. Take the cross product. Which is okay. So 2u, 2v and positive 1. Not sure why I got negative. And then I need put the parameterization into v. So 2y xc and then minus x. Then the flux through the surface is equal to, let's say du dv, is the dot product of those two. So here's the basic process from 4.5, which is given a vector field and a surface that's parameterized by r, we get the normal by taking the two partial derivatives, looking at the cross product to get something that's perpendicular to the surface, put the parameterization into v, take the dot product of the two. And this, as you can see, isn't very nice. It it isn't difficult because we're going to get things like 4uv and u cubes and e cubes and so on, but it's a bit tedious. So unless you really want to see it, I'm going to just do dot, dot, dot. So here's the basic one. So any questions on the process for the basic flux? You'd say it's in some ways similar to the line integral, which is we again get a parameterization, we plug it into the vector field. The difference is instead of just multiplying but taking the dot product with the derivative, we take the dot product with the cross product of the two derivatives. So let me do another of these. So the last one is kind of lazy. They didn't really say which way we were looking at it, so here's kind of the more specific one, where we actually have a surface. So we have a vector field, we have a surface, a cylinder without the ends, it's just the open cylinder. And where we want to find the flux out. And remember, that is kind of the base one, at least if we're going to do the next section. So like the last one, we will want to use the parameterization. So we have the cylinder of radius 5, which is this. So this one you actually have to get the parameterization. And as I said, the ones you should know are things like lines and circles and spheres. So how would I parameterize this? So in some ways, similar to a thing. So basically polar coordinates, it's just we know r is 5. So just to keep it as u and v, there's no reason I can't use thetas, but let me do it as it is 5 cosine of u, y is equal to 5 sine of u, and then z is any number from -7 to 7, so I'm just going to call it v. So there is our r. So again, we go through the same steps. We take the derivative with respect to u. Take the derivative with respect to v. Get the normal by taking the cross product, which is, these are all you should be double checking because I'm doing them fairly quickly. Let's see, is that right? Yes. Plug in U and V into my vector field. So minus y x and z. I should ask here what is, so z is going from -7 to 7, so v is going from -7 to 7. What are the limits for u? It'll turn out not to matter, but since it's polar coordinates, yeah, 0 to 2 pi. And now take the dot product. Can I get that? And this I can actually do, because what does this end up being? What's the dot product of those two? It's -25 sine cosine plus 25 sine cosine. So this whole thing is 0. Okay. So what I'm going to do now is let me make it into a problem from the next section. So let me keep the same vector field. And let me close it. So so you're going to be using this. And so let me, as I said, close it. So add on. So let's close it with disks at ±7 and ask what is the flow and orient it out still. And let's find the flux on that surface. And we can do this in two different ways. One way is I can continue with, and let me do one of these, because this is the simplified way from 4.5, which is by doing each of the three pieces. So we have the cylinder that we just did. So we found the flow on the cylinder without the ends is 0. And now we could find what is the flow on each of the ends. So let's make it say there's a D plus, which is equal to disk at Z equals 7. And let's find the flow on that. And then we'll do the other disk. So do this using the method of 4.5 and then using the method of 4.6. So for this one, in some ways it's the same as the last one, which is we can take the two derivatives, so we could parameterize the disk at z equals 7. And then we could take the partial derivatives and the cross product and do it. But this one, remember, I can just read off. Sorry about the hesitation there. I can just read off the normal, so I don't really need to do the cross product to get it. So for the disk at the top of the cylinder, what is the normal vector? Because think of your cylinder that's resting on just a flat surface, then the top of the cylinder, the normal will be pointing straight up. And here we're assuming z is equal to 7. So since we're going to take the dot product of this with the vector, when we put in the parameterization, the only thing we really care about is that last term. Right, so we'll do in a second. So yeah, so if it's oriented inward, it would be 0, 0, -1. Or if I do the disk at the bottom, that will also be 0, 0, -1, because it'll be pointing down. So we'll actually do one with 0, 0, 1 next, although I might not. So the vector with the parameterization. So in some ways, in this case, it would be u cosine v, u sine of v, where u goes from 0 to, I forget what the radius was, 5, right? So u would go from 0 to 5, and v would go from 0 to 2 pi, but we don't really care, because the only thing we care about is that z is equal to 7, and our v was, I have to go back and remind myself. V was negative y xz. I don't care. I don't care. And z is 7. So officially, our parameterization would be something like x is equal to u cosine v, y is equal to u sine v, comma 7. But since we're going to take the dot product with 0, 0, 1, we don't care about anything except for that last entry. And so we now have the integral over the disk of this whatever 7 dotted with 0, 0, 1, which is 7. And since that's a constant, it's just going to be 7 times the area of the disk. And the area of the disk is 25 pi, because it's a disk of radius 5. We still have needs by u. Well, sort of, as I said. So the idea is, for this one, we would do this. Let me write down. This would be our parameterization, where u goes from 0 to 5, because we want not just the circle, but the disk, so everything, the solid thing, and z is equal to 7. So in some ways, we'd be plugging those into those first two. But the last one, the vector was negative y comma x comma z. So when we plug in equals 7, well, we don't care about those first two terms, which do include the u's and v's. And then we can do the same thing for at -7. Same parameterization, except now z is equal to -7. And now our n is 0, 0, -1. And so you can see, well, we'd be getting the same thing. We'd have here, this would change to 0, whatever, -7, and dotted with 0, 0, -1. So it'll still be 0 times the area of t minus. And so this would, again, give us the 7 times 25 pi. And therefore, the flow through the whole thing would be the sum of those three, the 0 from the previous part, and then plus the 7 times 25 pi plus 7 times 25 pi, so whatever 25 times 14 is times pi. Okay. So this is using the 4.5 method. Let's go back. So doing this 3 different ways in some ways. So breaking this 11 up into lots of little pieces is, again, and let's call this closed surface. Well, call this. Yeah. It's closed. So we can use the divergence theorem, which is that the flow on M, which is the surface, is equal to the triple integral of the divergence. And this, you can write it either way. The second one is just a way of remembering what it is, which is it is the derivative of the first entry with respect to x plus the derivative of the second entry with respect to y plus the derivative of the third entry with respect to z. So since the first entry is going back and forth in my notes here, sorry about that. Is minus y. Derivative of that with respect to x is 0. Second entry is x. The derivative of that with respect to y is 0. Third entry is z. Derivative of that with respect to z is 1. So I get this. And here E is the solid cylinder. So you can see this is just going to give us the volume of the solid cylinder. And we know the volume of a solid cylinder is pi r squared times h. And r here was 5, so we get 25. H is, we're going from -7 to 7, so h is 14. And then times the pi. So staying with problem 11 for a while here. No, because that's, so here, this is the second way we could have done the original problem, which is we could have closed it with the two disks and then found the flow on the closed disk, which is this, and then found the flow on the two disks by themselves, which we did in the last slide. And for each of those, we got the 7 times 25 pi. So we found in the last part that the flow on the two disks together was the 350 pi. This is now saying this is the flow on the closed cylinder, which means that the flow on the cylinder without the top and the bottom is the 350 pi minus 50 pi, which is 0, which is what we got in the original part. No, because in some ways, the problem with picture that I tell you that one way of picturing flow is a river through a surface. But if you look at back the original vector field, you'll see it's kind of pointing in lots of different directions. So for example, the first term is negative y. So if y is a negative number, it's pointing in the positive direction. So it's a weird flow. So in this case, it turns out that the flow out of the top is actually the same, is positive, and the flow out of the bottom is also positive because things are kind of moving out in some ways. So in the normal world, if we're doing a river or something like that, if we put this into the river, the flow in one would be positive and the flow in the other would be negative. But with a generic vector field like this, there's no reason to have to. So this is the second way with the original problem. You can see this probably is harder than the original problem because it turned out that the dot product doing the 4.5 way is just 0, so everything fell apart. So this is 4.6. Which is that the flux integral is equal to a regular integral of this thing called the divergence. So any questions on this? So let me do one more. Which is number 20, still in 4.5. So this is in 4.5. So what they would really want you to do is to break it up into two pieces, parameterize the paraboloid part, which you could do as x is equal to u, y is equal to v, z is equal to 4 minus u squared minus v squared, where u and v go from 0 to 2. And then same thing with the disk. In the disk, z is equal to 0. And since it's at z equals 0, we have the out circle is radius 2. So we would have, again, the u cosine v u sine v, comma 0, where u goes from 0 to 2, and v goes from 0 to 2 pi. But since we know 4.6, this becomes easy. So what is this? What's the flow of this? So this is the flow through M of the v dot n ds. What is that equal to? Yeah, it's going to be 0. So this is about the divergence. Because it's the derivative of this first term with respect to x, which is 0, plus the derivative of the second term with respect to y, which is 0, plus the derivative of this third term with respect to z, which is 0. So we're doing the triple integral of 0, which of course is 0. So we put this in 4.5, but it really is, as a 4.6 question, really easy. Oh, so I'm not sure. So I think I have to check on Blackboard, but usually what we do in this class for finals is you have at least 3 finals on Blackboard, and so we treat that as a review. Because in some ways, me writing a review isn't as good as just looking at an old final, because I only write part of the final, so you want to look at one that's written by other people. So any questions on this? So this is 4.6. So obviously, we're going to do more examples. So we'll do that Monday. But let me kind of finish out the material, and let's quickly look through 4.7, which is another way of doing things. The same thing. So Stokes' theorem is a way that relates a line integral to a flow. So this is the line integral on the boundary of M. So here, M is, again, a two-dimensional surface in 3 dimensions. So if I look at the boundary of that, which I'll do in the next example, in the one example we're going to do, then that is the same as this is the flux of the curl. So this is the curl of, here I'm using F. So in some ways, this is the base one, but the one that we usually use is actually a lemma to this, because this says if we have the curl on a two-dimensional surface, it's equal to the line integral on its boundary. But that, if you think about it, implies that if two surfaces have the same boundary, then they're going to be equal, because they're both equal to the flow, the line integral on the boundary. So this is the base one, but the one that we usually use is this lemma. So if two-dimensional surfaces in 3D have the same boundary, then the flow of the curl through them is the same. And let me do just the one example, because that's about how much time we have. So here's a vector function. So kind of an aside, because we use this a little bit, but let's go back and just say what is the curl of this thing. And we know from the conservative section it is this, where this is P, this is Q, this is R. So I take the derivative of R with respect to Y, which is x e to the xy, derivative of Q with respect to Z, take the derivative of R with respect to X, minus derivative of P with respect to Z, derivative of Q with respect to X, and derivative of P with respect to Z. Remember, the way we used it before is if this was 0, it would be a conservative function. So obviously this is not. Okay, so this really isn't the part from this section. This is really a reminder of stuff from before. But any questions on this? So let me do the real problem. lost squares. So let me just make one up. Oh, yeah, so the gradient. So remember that this thing is just a curl. So this is supposed to be a way of remembering how you get it. So if you want to just call it the curl, you can. So the way you would get it as a reminder, if you don't remember what it was from the last one, it is you make the first row into partial x, partial y. Well, first one into ijk. Second entry is partial x, partial y, and partial z. And the last row as p, q, and r. And then get the determinant. And that will give you what I had in the last one. So let's find what is this. And we want to find the curl the flow of the curl on this surface. And what Stoke's theorem gives us, if I try drawing this, and I get, there's the paraboloid, up through this is equals 2. And I can see that this is the boundary. But notice the boundary, this is also the boundary. Oh, that went well. It's also the boundary for that little disk. It's this. And so Stoke's theorem says instead of doing it on the original M, which we'd have to parameterize and then take the cross product and then plug it into this curl thing, instead I could do it on, so let's call this D. So this is equal to by Stokes and now going back to 4.5, we have the thing, well, I can read off what is n in this case, and this is, I forget if I said, oriented up. And so this is where the compatible part comes in. So obviously it's either going to be the 0, 0, 1 or the 0, 0, negative 1. And the compatible part says, and let me look at this disk from above. The compatible one vector is by the right-hand rule. So if I curl my fingers in the direction of that arrow, my thumb is giving me the direction that's compatible. So since the paraboloid is up, that means that the flow must be going around counterclockwise. And so that means on the disk, we have the same thing. It's still going around the disk counterclockwise. And therefore, again, the orientation must be up. So in this case, it's different from the divergence where we wanted stuff out. Here it has to be compatible. So we're going from the paraboloid to the disk. We need the normal on it to be compatible to the original one. And you can see I made this fairly nice because if you look back at the curl, I got something messy, and -1. So the parameterization is just I don't care, and -1. And so therefore I'm getting this double integral over the disk of the whatever, -1 dotted with the normal vector. And so I'm just going to get -1 times the area of the disk. And the only thing is, so when z equals 2, it is radius 2. So this would be, sorry, -4 pi. So this is the quick run through for Stokes' theorem, which says if I have two surfaces that have the same boundary, then the flow of the curl will be the same for both of them. And so I can take something somewhat complicated like this paraboloid. Notice it has the same boundary as this disk, and know, well, on the disk, it's simple. So this part B, this is, in this class, the way that we usually use the Stokes theorem. We could have also gotten the line integral of f on the boundary, the circle, but in this case you can see this way is easier. So in some ways we're still writing the final, so I'll let you know on Monday if we have to worry about this. So if we do have to worry about this for the final, I'll do 1 or 2 more examples on Monday of this. If not, I'll just tell you you can ignore it. So the final will still be written. So I'm not quite sure. I'm guessing not, but not completely positive yet. So any questions on this? So probably in 2 or 3 hours, I'll put a mock quiz, which will include this, but this you can treat as something you might not have to do. So I'll put a mock quiz up, and then tomorrow I'll put up answers. I should also, again, apologize. I don't have your tests. As I said, I probably wouldn't yesterday, but I should have them Monday. The answers are up, so if you're curious about that, you can look at that. You should still have your actual test, so you can see about how well you did. No. So what I said was, so we're done with quizzes. So we had the 5 quiz grades, but this stuff from 4.5, 4.6, and now this last thing haven't been on a quiz or a test. So in those set situations, what I usually do is say, well, here's a quiz that could have been written for it, but it's not going to count. So any questions on this? Okay, so the usual thing. If you don't have any questions, we're done. Have a good weekend. If you do have any quick questions, I'm going to stop recording, but I'll stick around and you'll let me know.